So today we're going to talk about environmental factors that increase the risk for Parkinson's disease. Now, last week or last month, it seems like time flies so fast, seems like just yesterday. I spoke about the genetic factors that are associated with Parkinson's disease, and in this era of great advances in medical genetics and sequencing the genome, and the finding of at least 12 different genetic mutations that increase the risk of Parkinson's disease, we tend to overlook the importance of environmental factors that can cause a Parkinson's syndrome and indeed Parkinson's disease. So I'm going to just right at the outset let you know that of all the factors that can result in Parkinson's syndrome, I'll call it Parkinson's syndrome because Parkinson's disease is just a subtype of Parkinson's syndrome. But of all the factors, the genetic factors account for only 10% of the risk of developing Parkinson's disease or Parkinson's syndrome. 80% to 90% is due to environmental risk factors. And I'm going to go through a bunch of them, especially the more important ones that have shed light on how Parkinson's disease develops. And in fact, if it wasn't for some of the discoveries from about 1983, how a chemical in the environment resulted in Parkinson's disease, I wouldn't have become an expert in Parkinson's disease. I trained as a pharmacologist, neuropharmacologist, and I decided to focus on Parkinson's disease when a chemical called MPTP, which is very similar to a pesticide, herbicide used in the United States and other parts of the world, when that chemical was contaminated, was a contaminant in an underground synthesis of Demerol and sold as heroin substitute in San Francisco in early 80s, there was a little epidemic of Parkinson's disease in young IV drug abusers. And I was doing a neurology residency when that came out in the journal Science, which is one of the preeminent science journals, named Science appropriately. And it was a remarkable thing because it was the strongest evidence that small chemicals could destroy dopamine neurons and produce Parkinson's disease, which is slowness of movement, cognitive rigidity, tremor, that gradually worsens. And these are young people in their 20s and 30s who happen to be drug dependent, opiate dependent, and we go through periods of epidemics of opiate abuse. There's another opiate abuse epidemic, but it's due to prescription opioids. But in the 80s, there was a big epidemic of IV heroin use. Heroin is a very potent opiate drug. And this underground chemist was making a synthetic opiate known as meperidine or Demerol, which is a commonly used painkiller. It's a synthetic opiate. It's not derived from the poppy plant like morphine, heroin, etc. Demerol is made in the lab, and it acts on the same receptors that morphine acts on. So you can't tell the difference between meperidine or Demerol and morphine. Maybe the duration of action and latency of onset. So it was being sold as a new kind of heroin. They called it China White. And meperidine is not a difficult synthesis. So you could make it in your underground lab. So a chemistry student set up a lab in his basement and was making a lot of synthetic Demerol or meperidine. And unfortunately, he was not really such a great chemist and didn't purify his product, and it was loaded with a similar compound called MPTP. That's an acronym for, I love to tell you what the acronyms are. It just refreshes my memory because once you get over 60, you tend to lose things like that, so I constantly rehearse. So it's methylphenyl tetrahydropyridine. It's easier to say MPTP, but I like to say it, keep my memory intact. So it's a chemical that has certain similarities with Demerol, but it's similar also to an herbicide called paraquat that you may have heard about. So this report came out, and I was intrigued by it because my PhD work was on opiate dependence, where morphine acts in the brain to produce tolerance and dependence, and when you stop using it, you have a withdrawal syndrome. So I was studying where in the brain morphine acted to reduce dependence. So that was my background before I went to medical school. So I did a PhD first, then I did a PhD at MD, and when I was doing my neurology training after medical school, I came across this paper. I had no idea whether I'd go into psychiatry or neurology at a certain time. But then I realized I should focus on Parkinson's disease because I could apply my knowledge about opiate pharmacology to agents that can cause Parkinson's disease, which is an opiate similar to opiate drugs. And opiate drugs act on dopamine systems. They act on the dopamine reward system. You know, we have two major dopamine systems. The nigrostriatal dopamine system, which is responsible for the automatic execution of learned movement. So you don't have to think about moving because it's mediated through this system. And dopamine, nigrostriatal dopamine, is just one little link of the basal ganglia that executes normal movements. But then there's another dopamine system that's more in the middle of the brainstem and projects to the limbic brain, the emotional brain, and it's responsible for feelings of well-being, for pleasure. Whenever you feel good about something, there's a little tweaking of the mesolimbic dopamine system. The pleasure part of the brain is also mediated by dopamine. So you can imagine if morphine acted on the dopamine pleasure system, which it did. That's why people want to do it over and over again. When something feels good, you want to repeat it. That's the nature of it. Something feels bad, you want to avoid it. This is what is present in all animals. You want to repeat experiences that are rewarding, make you feel good. And dopamine system is very important in that. So the Demerol analog, I thought, was going to interact with the mesolimbic dopamine system, and it's interesting that it's poisoning the dopamine nigrostriatal system. So that's when I started to do research on environmental toxicants that can destroy dopamine neurons, and that's what I ended up doing for the first 12 years of my career. I got a grant from NIH to look at environmental toxicants that can cause Parkinsonism. So I'm going to talk a bit about the chemicals and what we've learned about MPTP. But before MPTP, and soon after James Parkinson described his story of observing 8 patients. Now, James Parkinson never actually had patients in his practice that had what he called paralysis agitans, known in Old English as shaking palsy. He just observed people in his neighborhood walking down the street with shuffling gait, one arm not swinging, trembling, and he noticed them. And he wrote about them. But they weren't his patients. But because he was the first one to describe so carefully what they looked like and how they walked, that eventually, about 50, 60 years later, the French neurologist Charcot named the shaking palsy Parkinson's disease in his honor, because by then, by late 19th century, everyone had recognized this syndrome, and it seemed to be increasing in frequency. And in fact, talking about environmental factors, with the rise of the Industrial Revolution, with greater pollution everywhere, there was more and more of the disease. And if you notice, around the world, the highest frequency of Parkinson's disease are in the highly industrialized nations. So you had a hint that environmental factors, pollutants, chemicals, can result in Parkinsonism. Secondly, a guy named Cooper was the first to report what he called a disorder that was similar to paralysis agitans. He described this about 20 years later than James Parkinson described Parkinson's syndrome, or paralysis agitans. He described in manganese ore crushers a syndrome of rigidity and tremor that looked just like Parkinson's disease. So it was called manganese-induced Parkinsonism. So that was another kind of chemical that finally a substance was identified that could produce and mimic a syndrome of Parkinsonism. In fact, this is something I also investigated, was heavy metals that can produce Parkinsonism. And many epidemiological studies done more recently show that people who work with heavy metals, people who work in smelting, welders, pipe fitters, anyone who works with these heavy metals has a higher risk of developing Parkinson's disease. And in fact, I was a consultant for a big medical legal lawsuit that the Welders Union brought against General Electric, because General Electric was the owner of these welding rods that have manganese. Now, when people weld, they like to weld, you know, when you fuse two metals in an oxygen-free environment, because if oxygen gets into the weld, it'll oxidize and make it weak. So they always coat the welding rod with manganese, and when manganese burns, it sucks up oxygen. And it leaves it up manganese oxide fumes, and so the weld is very clean. So routinely, it was called Lincoln Electric, was the maker of welding rods since the 19th century, bought by General Electric. And more cases of welders who develop Parkinson's syndrome, just like Cooper described, manganese ore crushers develop Parkinsonism. So there was a lawsuit. I think examined about 200 patients over many years, wrote an article about how manganese can produce a Parkinson's syndrome. There's some differences from Parkinson's disease. They both cause dopamine neuron loss, but the manganism also destroys downstream, so they don't respond as well to levodopa. That's how, so you call it, it's a Parkinson's syndrome with rigidity, slowness, and sometimes psychosis and dementia. And this was described even earlier, the beginning of the 20th century, in Chile, where manganese miners were known to develop locura manganesa, manganese madness. And these workers in the mines where manganese was being taken out would sometimes develop psychosis. But if they were taken out of the job for 2 months, it would clear up. But some of them, even though they were cleared of that environment, would develop Parkinson's syndrome. So it's another example of a population of people, besides welders, they're the miners, the ore crushers, who had heavy metal-induced Parkinsonism. Anyway, to make a long story about this case, it was eventually settled between the union, the welders, and the General Electric. I had to testify a number of times about it, and it was, who made the big bucks were the lawyers, unfortunately. I think many of the welders, yeah, that's how it is when you do a class action suit like this. And one of the things that the lawyers told me I had to do was destroy all the records of the cases. That was part of the agreement. So it never went to the final court, it was a settlement. So all of my records of the exams that I did, etc., all the documentation I had related to this case was destroyed. However, I published a significant paper on the topic before the settlement was made. So it's well known. It's well known that manganese, why were they suing General Electric? Well, because the toxicity of manganese was already known by 1910, 1915, 1920, but Lincoln Electric and then General Electric never put warnings that you could develop a syndrome of Parkinsonism unless you use protective equipment. And you know, welders are very macho. They don't wear the breathing fumes. They work, especially pipe fitters or boiler makers. They go into or shipbuilders. And that's where all these welders, it's amazing how many people suffer from Parkinsonism who are welders. So anyway, that's one example. But then people who work with other metals have a higher risk of developing Parkinsonism. Besides heavy metals, there's also evidence that chemicals like MPTP, and that's what I did a lot of research on, and I began to look for chemicals similar to MPTP and found one in particular. The way it gave me the lead, the way you do this, how does one approach this problem? Well, you can grow in the lab. We grew in the lab cell cultures that are dopaminergic, and this is prepared from mouse or rat fetal brain tissue. You take out their midbrain that has these dopamine neuron progenitors, and you can grow them in culture dish and keep them as dopamine neurons, so they're always the same, and they're very sensitive to different chemicals. So you could test by putting into the culture dish different concentrations of a whole bunch of chemicals. And you find the chemicals that destroy those dopamine neurons. So that's how we did it. So, but I found a lot more chemicals that destroy dopamine neurons. So I figured another approach would be to look at the brains of people with Parkinson's disease from the University of Miami Brain Bank, which I was doing this when I was at the University of Miami. And I collected brain tissue that had also the clinical record that corresponded in life to the postmortem tissue that the patients had donated for research. And also looked at Alzheimer's disease brains that were in the brain bank, and also normal age-matched controls. Those are the hardest ones to find, because people who are healthy are not going to donate their brains. Usually people have a disease. But fortunately, we're able to get other normal brains from other brain banks. And all we need is a little bit of tissue. I didn't ask for the whole brain. So getting the control tissue was the hardest. The Parkinson's brains, the Alzheimer's brains were easy. And we screened with the toxicology lab for 20 different chemicals. The ones that we focused on were those that tend to stay in fat tissue for a long time. So these were pesticides especially. They're organochlorine pesticides similar to DDT. Once they're in the body, they accumulate in fat tissue and they'll stay in your body for life. And the brain has a lot of fat. Myelin, that is the insulator for nerve fibers, is fatty tissue, and these chemicals are retained there throughout life and into death, so I can measure them. And we found that every brain we looked at, normals, Alzheimer's, and PD, all had DDT. So we're all exposed to it. It may cause a lot of problems in animals, but it didn't cause either of these illnesses. The one that was surprising, that was found only in the PD brains, not in the Alzheimer's and controls, was another pesticide called dieldrin, which was banned in 1960s or so because it was produced, it was just like DDT. It was harmful to birds and their eggs. They had weaker shells, and it was believed that it might cause a liver cancer. So it was banned. But though that dieldrin was found in Parkinson's disease brains, even though dieldrin has not been allowed to be used in the United States for such a long time. But I found out that dieldrin is still used in many other countries, and that we make dieldrin and sell it to foreign countries, and they put it on their products like grapes, and we bring the grapes and we eat the grapes. So this is, I don't want to point fingers at Dow Chemical, but unfortunately that's who, and I think finally they stopped making dieldrin. But dieldrin was a very interesting lead compound. Because of that finding, we applied, the Department of Defense was very interested in why so many people were getting ALS who had been in Desert Storm. A lot of veterans coming back from war in the Middle East. We already knew about Agent Orange in Vietnam and how that can increase the frequency of Parkinson's disease. But there was an increase in ALS, not so much PD. But I wrote in the grant that I would look for not only dieldrin, but also a whole bunch of other chemicals that we found might be toxic, including that might be found in the Middle East, as these fungi that grow in arid environments make chemicals called rubatoxin, ochratoxin. And they, in the cell cultures, destroy dopamine neurons, and in mice cause a Parkinson syndrome. So I was able to get funding from DoD, and we wrote a very, like a white paper summarizing all the chemicals that can produce Parkinsonism. So we thought ochratoxin was one, dieldrin is the other. Those are the two most important ones that can cause the demise of dopamine neurons. Now, so I'm going to stop talking about that part of it, but we'll point out that MPTP isn't what causes Parkinson's disease that we see in all of us. But by studying how MPTP killed dopamine neurons, we learned something about mitochondrial function in run-of-the-mill Parkinson's disease. One of the ways that MPTP is toxic to dopamine neurons is that it's broken down by monoamine oxidase, once it gets into the brain, into something called MPP, methylphenylpyridinium. And MPP looks like dopamine to a neuron, very similar structure. once it's metabolized. MPTP doesn't look like dopamine. It gets into the brain makes it into MPP. MPP sees, oh, that's some dopamine, I'll suck it up through the dopamine transporter, and once it's in dopamine neurons selectively, not in all neurons. These toxins are selective. They don't destroy every cell. The selectivity is based on the fact that it looks like dopamine when it's metabolized, this MPTP. So it accumulates in those neurons, and then it's taken up by the furnaces of the cells, called mitochondria. And in mitochondria, it inhibits the production of energy. It blocks electron transport, which is like the you know how hydroelectric power, when water falls down by gravity, it turns turbines and generates electricity. It's a similar thing when electrons are transported from one cytochrome to another, they generate molecules of energy. Well, MPP blocked the turbines. It blocked the energy producing system in mitochondria. And that's how it killed cells. So from that point on, we said, well, does Parkinson's disease itself have a problem with mitochondria? Lo and behold, the clue, what pointed the finger to mitochondria in Parkinson's disease, was the research with neurotoxicants. This is how advances in knowledge occur. So we get a clue from a pesticide or an opiate drug derivative or a pesticide. By the way, the dieldrin and ribotrypsin also interfere with electron transport. So they're all mitochondrial toxicants. So we realized mitochondria are important, but no one had ever thought of mitochondria as being a key feature in Parkinson's disease. I'm talking about the human Parkinson's disease. So that led to studies into mitochondria function in people who have Parkinson's disease. And there are different ways to look at mitochondrial function. There's actually something called MR spectroscopy that you can do in muscle, in brain, and sure enough, there's a metabolic energy production problem you can see by MR spectroscopy in the brains of people with Parkinson's disease. That led then to a whole new kind of treatment that unfortunately didn't work very well, was to give mitochondrial enhancers, mitochondrial cocktails to Parkinson's patients. And one of the key agents is coenzyme Q10 that many of you will probably still continue to take. The other is to give a lot of vitamin E, any kind, because as you fail to make ATP, which is the currency of energy that all cells use, you generate free radicals. If it's like the carburetor is not working properly, combining oxygen with the fuel, you get a lot of fumes, toxic fumes. So you generate a lot of, when the mitochondria don't work, you get a lot of toxic oxyradicals. And so the key in a mitochondrial cocktail was to give an enhancer of electron transport that improves energy production and also scavenges and protects against the free radicals, the oxygen radicals. And we still recommend that you take antioxidants, but you don't have to take the 2,000 units of vitamin E. We suggest you take vitamin E, coenzyme Q10, plenty of antioxidants. It doesn't really stop the illness like we hoped it would, but it probably is good in the long run. It's good for general health. So we haven't yet found how to really improve mitochondrial function back to normal in people with Parkinson's disease. I pointed out because we learned about this by the study of these environmental toxicants that produce Parkinson's syndrome. But besides chemicals in the environment, from fungi, from man-made chemicals, from heavy metals, we also have other causes of Parkinsonism. And one of the biggies that resulted in an epidemic of Parkinson's disease were viruses. And none of you probably, my mother was born in 1910, and actually my grandmother died in the post-encephalitic, during the epidemic of the sleeping sickness, which is a worldwide epidemic of a flu, probably a bird flu, but no one really knows, that would cause serious encephalitis, swelling of the brain, and if you survive that, you could develop Parkinson's disease. So there's a whole generation of people who had post-encephalitic Parkinsonism caused by a virus that was very severe, that was new to the humans, that had jumped from chickens or pigs, we don't know, to the humans, and caused a worldwide pandemic where a lot of people died. So my father's mother died about 1919 because of the encephalitis. I didn't know that until I began talking to my father about how she died, and it's kind of intriguing. But so, in some of the earliest work with levodopa was done in patients that were in nursing homes who had had post-encephalitic Parkinson's disease caused by virus. The movie Awakenings that Oliver Sacks wrote about his early experiments in treating post-encephalitic Parkinson's disease patients with levodopa was very dramatically effective. That was the first evidence that dopamine replacement was going to be helpful. And we only learned about the dopamine loss in the 50s when drugs that were given for psychiatric conditions were causing Parkinsonism, but not permanent Parkinsonism. Unlike the toxicants I told you about that destroy dopaminergic neurons, there's a whole class of medications that were developed for psychiatric conditions that can produce a syndrome of Parkinsonism that's reversible. And when this was done in the early 50s, it was found that thorazine was the first one, chlorpromazine, shown to produce a syndrome of Parkinsonism in young schizophrenic patients. If you lowered the dose of thorazine, Parkinsonism would go away. A guy who won the Nobel Prize for work, a guy named Carlson, a Swedish neuropharmacologist, found that thorazine blocked the actions of dopamine. And that's how it was good for, but it blocked all dopamine receptors, so it made people anhedonic, means they could experience no pleasure. But it's a great thing for people who have racing thoughts, paranoia, delusions. It's an antipsychotic drug. So it would be great for schizophrenics. Side effect was it also blocked movement. So here are these young schizophrenics, no longer hallucinating, shuffling down the hallway with drooling. This was very common side effect of the major tranquilizers in the 50s. Carlson found that it was a problem with blocking dopamine, and so he began to measure. He said maybe Parkinson's disease had something to do with dopamine, because no one knew that. We knew that a whole bunch of things could cause Parkinsonism: viruses, heavy metals, chemicals. And he found that people whose brains were examined, who in life had Parkinson's, didn't have any dopamine in the nigrostriatal system. So that led to the idea, well, if we replace dopamine, that was in the 60s, and the first group of patients that they tried were these post-encephalitic Parkinson patients, and it was effective. And that's led to the mainstay of treatment, which is levodopa, carbidopa, Sinemet. And then to advance further, we found we can make artificial dopamine called dopamine agonists, like Mirapex, Pramipexole, Requip, bromocriptine, all of those, that act directly on dopamine receptors to alleviate symptoms of Parkinsonism. Again, all of this information that we've learned about Parkinson's disease come from research on toxicants that cause Parkinson's disease permanently, or drugs that produce temporary Parkinsonism. So it's pretty amazing. You can see why someone like myself, who was really a neuropharmacologist, became so interested in Parkinson's disease, and still have the interest in it. There's a bunch of other factors. Notice I haven't talked about genetics, because I spent all my time talking about it. But you have to realize that we are who we are, and each disease is determined not just by what you inherited, what your physiology is that runs in the family, but how you metabolize these chemicals is genetically determined. So you can have no mutations that increase the risk of Parkinson's disease that affect neurons, but if you have mutations in the liver, they may make you more vulnerable to certain chemicals that normally people would break down. But if you can't break down certain chemicals, it might result in some toxic materials that build up and cause Parkinsonism. So it's a very complex issue, the interplay of genetics or heredity and environmental exposures. And there's another really fascinating environmental factor that increases the risk for Parkinson's disease, and we're seeing more of it. And I'm starting to look at this a bit more. And it has to do with head trauma. Head trauma, if you look at epidemiological surveys that look at risks how you determine risk factors for Parkinson's disease is to get a population of people with Parkinson's disease, a population of age-matched controls that don't have Parkinson's disease, and do extensive surveys of their dietary history, their other medical problems, a number of things like that, whether they've had head injuries, did they lose consciousness, etc. And one of the big factors that shows up in Parkinson's disease more than age-matched controls is head trauma. Now, it's epidemiological. It doesn't say cause and effect. There's an association between head trauma and Parkinson's disease. And we've noticed so many patients, when I started off doing a fellowship in movement disorders, that many patients with Parkinson's disease believe that their first symptom became evident after a car accident or after some head trauma. So we began, and many people have actually, started lawsuits because they claim that the accident caused their Parkinson's disease. So Dr. Weiner and I wrote a review article of head trauma and trauma as a cause of Parkinson's disease, and we concluded it isn't a cause. It's often associated. In fact, almost any stress, hearing of the death of a loved one, can allow the symptoms to become evident. So because Parkinson's disease doesn't begin like that. It doesn't begin immediately after a head trauma. There's an insidious loss of dopamine that begins from the age of 40. And when you've lost 75% of the dopamine, you're on the verge of having the first symptom, even though you've lost so much dopamine. And all you need, so the radio's on, but the volume is too low, you're not aware of it. The stress is turning up the volume, and then you see the symptoms. That's how we interpreted trauma, as increasing the risk for Parkinson's. It just allowed it to become manifest. However, we established certain principles. If the head trauma resulted in loss of consciousness and an MRI of the brain showed that there was damage to the midbrain or striatum, and then you developed Parkinsonism, that case of trauma would be a very easy cause and effect case. But that's very rare that you get that evidence following a head trauma. But what about trauma that is just repetitively over many years, like football players and boxers? Well, we know for sure that chronic traumatic encephalopathy will produce features of Alzheimer's disease, dementia. But it really doesn't produce Parkinsonism. Everyone says, what about Muhammad Ali? Well, he wasn't hit very much in the head. He really wasn't. He was an amazing boxer in his ability to avoid getting hit in the head. He would dance around, float like a butterfly, sting like a bee, So I actually met Muhammad Ali when I was in Miami, and I spoke to him and so forth. He really did not have, he had young onset Parkinson's. He had all the classic features, including when they gave him levodopa, he developed, as young onset Parkinson patients often do, they develop dyskinesias very quickly. And his dyskinesia was a grimacing of the face. And he was horrified because he wanted to look pretty, right? He's very proud of his appearance. And he didn't like that. When he took levodopa, he started grimacing. And so he went for years without taking any medication. I finally persuaded him to take a dopamine agonist, Pergolide, that didn't produce the dyskinesia. So he finally got a little better. But he went for a decade or so without taking any medicine. And there's a famous almost meme of him holding the torch for the Olympics, and he saw the tremendous tremor, and he lost his voice, he was whispering, etc. But so head trauma is something that we're looking at now in terms of mechanisms that are involved in repair of injuries sustained by head trauma. And so far we haven't seen evidence that the head trauma causes Parkinsonism, even though epidemiologically you'll see that it's one of the risk factors for Parkinson's disease. It's a much greater risk factor for dementia. And the one famous case, Hernandez, who killed someone, he's a New York Jets receiver, committed suicide. They looked at his brain, and his brain was shrunken. He's only 28 years old. It looked like an Alzheimer's brain, and had all the amyloid plaque and neurofibrillary tangles that Alzheimer's brains have. So we know that chronic traumatic encephalopathy can cause precipitation of these proteins and dementia, but not been associated with Parkinson's disease clearly, except for those very specific cases where there's been injury from an acute head trauma that's pretty serious in a car accident. and we can document that by MRI. But otherwise, I wouldn't be concerned about head trauma causing Parkinsonism. There's another really interesting clue about the environmental cause of Parkinsonism, because that's a topic, environmental factors. And the Lewy body, which is the hallmark, pathological hallmark of Parkinson's disease, is found in two regions of the brain way before symptoms develop. Two regions of the brain where nerve endings from the environment, the nose, the smell, olfactory nerves, go to the olfactory bulb, responsible for smell. And Lewy bodies appear in the olfactory bulb really early, and it's associated with loss of the sense of smell. And the Lewy bodies are also found in the bottom of the brainstem, in the vagal motor nucleus. And the vagus nerve is the one that goes to the stomach and intestines. So the concept is that something we're eating is getting into the vagus nerve and going back and accumulating in the vagal motor nucleus of the brainstem or in the olfactory bulb. So something we're smelling or eating is accumulating and is transported up and result in the formation of Lewy bodies. And once those Lewy bodies are in the central nervous system, they disseminate, they begin to spread. Because if you take Lewy bodies and inject it into one part of the brain in an animal, after some time you find it distributed throughout the brain. So there's clearly some things in the environment that we either sniff or we ingest that result in Lewy bodies in those front of the brain and the rear of the brain that gradually spread and cause Parkinson's disease. So the evidence that environmental factors cause Parkinson's disease is very, very strong. Starting with the rise of the Industrial Revolution, we knew that pollution is an important component of I guess, it's not only caused Parkinson's disease, I'm sure, but a whole bunch of other conditions from lung cancers, liver cancers, etc. A lot of cancers are due to environmental pollutants. And then the chemicals we use to kill pesticides and to kill pests or plants can also destroy dopaminergic neurons. That's a second major kind of cause of Parkinsonism. And finally, we know that viruses, I'm concerned that eventually we're going to get another epidemic of encephalitic disease that can cause Parkinsonism, because these things come every few hundred years. And every time I hear an epidemic in China from bird flu, I'm always a bit concerned. I was asked to write a chapter in a book on viruses that can cause movement disorders. And there's like West Nile virus, for example, which we can get through mosquito bites, can cause Parkinsonism. Probably we have some cases of Parkinsonism that I see here, but no one's going to remember having a fever and malaise from this mosquito bite because you think, oh, it was a cold. That's what it feels like. And then you go on to develop this. So I think there are viruses still that we're all exposed to, especially in this area where there's so many mosquitoes, that might be associated with Parkinson's disease. A number of other viruses besides the West Nile virus. And I'm going to end it here. Yeah.
You didn't mention anything about mercury?
Mercury doesn't cause Parkinson's disease.
Wow.
It causes cerebellar ataxia. And it's not the mercury in your tooth filling, so don't get them all removed.
Right.
And it's when mercury is in an organic holder, and when it's, for example, there was a big epidemic in Japan called when mercury was from a factory was let out into the bay, and the fish would accumulate it and accumulate in an organic form in fish flesh and liver. And people would eat that fish would accumulate mercury, and mercury accumulates in the cerebellum and causes ataxia, but no Parkinsonism. So there was a period where because I would write about different metals and movement disorders they can cause. They say, should I have my teeth pulled? Right. Get all these fillings removed? No, it's not necessary. That mercury amalgam is not toxic. No one uses it anymore anyway. There's too much fear about it. So I guess that's it. I'm sure you'll have other questions, but I can't answer them because I don't have all the answers.